Swayam Prabha. Digital India. Educated India.
Now, let us ponder a little bit more on the Mohs circle. Let us say that I have this is a normal stress axis, this is the shear stress axis sigma xy, okay, and let us say I have a circle. Now, the center of the circle is this point and these points represents the extremum normal stresses sigma xx max and sigma xx minimum, and this line represents sigma xy max similarly this is sigma xy max, okay, and then you add a stress state which was somewhere here, okay, that was a stress state that was given to you, say this is sigma xx, sigma xy, and this will be sigma yy comma sigma xy minus, okay. So, that was a stress state that was given to you, that is I have Ex, Ey, on this I have a stress element which was sigma xx, sigma xy, this is also sigma xy, and I add this is sigma yy like this. Now, I want to represent what happens on this circle when the coordinate system rotates by an angle theta. Now, this is Ex star, Ey star, I have given a anticlockwise rotation of theta, okay. Now, if I write the equation of this circle as x plus x naught whole square plus y square equal to r square and do a transformation x equal to r cos phi and y is r sin phi, and if I use 0 to 360 as the domain of phi, 0 less than phi less than 2 pi as a domain of this phi, then what is x? How is phi measured? Phi is measured in a, let us say I have a plane oriented like this, okay. The phi is measured, I will give two options, one is this phi or is this phi, let us call as alpha, and let us call another angle which is this. Is alpha phi or beta phi? There is a question, is alpha phi or beta phi? Let us see, if phi is more than 90 degrees, x would have negative value, here x has negative value, y has positive value. So, beta is phi, so phi is beta, okay. So, basically now what does it mean? It means that from this stress state I have to rotate by a clockwise angle of beta to reach the x axis, that is what this phi means. Similarly, here in our problem your x is nothing but sigma x star and in that case you add the expression sigma x star as sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta, or this is nothing but r this plus sigma xy sin 2 theta is r cos phi, where phi is 2 theta. 2 theta is the angle measured clockwise from the plane to another plane. Okay. So, basically now if I rotate this by angle theta, what I should do is from here I have to rotate clockwise by angle 2 theta. Theta is the actual rotation. So, I have to go from this plane to this plane by angle 2 theta to get into the stress coordinates for Ex star Ey star. So, this will be, this point would be sigma xx moves on to this point. So, this will be sigma x star sigma x star y star, and this point would be sigma y star minus sigma x star y star. Okay. So, that is how you have to construct the Morse circle. Okay. So, from a given plane you rotate in the clockwise direction by 2 theta, if the rotation of the coordinate system is in the anticlockwise direction by an angle theta. The coordinate system rotates in the anticlockwise direction by an angle theta, the Morse circle corresponds to a 2 theta rotation from the plane to the new plane. Okay. So, this will be angle 2 theta rotation there to get into the new stress state. Okay. So, this is how you use the Morse circle equation to find the stress components in a rotated configuration. Okay. So, what we have seen till now is we have seen how to find sigma xx max, sigma xx minimum, sigma xy max, okay, and how do you represent two stress states on the Morse circle, wherein the coordinate system has been rotated by an angle theta in the anticlockwise sense. That is, for this if I were to represent sigma x star, sigma y star and sigma xy star, it will be like this. This is the stress cube, this will be sigma x star and this will be sigma x star y star. And this will be sigma y star. Okay. So, that is how you will represent a cube wherein the coordinate system has been rotated in the anticlockwise sense by an angle theta. Okay. Next, let us look at a practical problem. Say I have this plate which is subjected to the following stresses. I have, say this is 10 MPa and I have a normal stress 5 MPa, I have a shear stress 3 MPa. Okay. And let us say I have a weld here. This plate is, this is that is weld. Okay. I want to ensure that this weld does not fail under this given state of stress. Okay. The weld does not fail under the given state of stress. So, how will a weld fail? The weld will fail by these plates sliding against each other, that is a shear stress developing on the surface of the weld is being more than what it can withstand, or it can separate out like this wherein the normal stress exceeds a particular limit that the weld can withstand. Okay. So, what I am interested is, I am interested in finding the following. I am interested in finding the component of stress sigma normal to the weld surface. I am interested in finding the shear stress tau of n, where n is, this is n, the normal to the weld surface. Okay. So, how do I find sigma of n? Sigma of n is sigma times n dotted with n, sigma transpose times n dotted with n, or is a traction on that face dotted with n. Okay. Now, what is sigma for this? Sigma would be 10, 3, 0, 3, 5, 0, 0, 0, 0, right. I have chosen this as my coordinate system Ex, Ey. Now, let us say the weld makes an angle of theta here, theta equal to 30 degrees. Okay. Now, what is n then? I have Ex, Ey, I have a surface and I have the normal n, this is normal, and I know that this angle is 30 degrees, then I will know that this angle would be 30 degrees, and hence my n I can write it as sin 30 Ex plus cos 30 Ey, right. Okay. So, I represented both n, I represented both the normal and the stress tensor using the same coordinate system Ex, Ey, using the same coordinate system Ex, Ey. Okay. So, now all that I have to do is do this matrix multiplications to get the normal stress, that will be 10, 3, 3, 5, 0, 0, 0, 0, 0 into sin 30 cos 30 0 dotted with sin 30 cos 30 0. So, this will be 10 times sin 30 plus 3 times cos 30, 3 times sin 30 plus 5 times cos 30 0 dotted with sin 30 cos 30 and 0, which will give me 10 times sin square 30 plus 5 times cos square 30 plus 3 times 3 into 2 cos 30 into sin 30. Okay. That will be the normal stress. You can do what this value is and that will be your normal stress. Now, how do I find the shear stress? That is the question. Now, how do I find the shear stress tau of n? That is the question. I will give you an expression in 3 dimensions. Now, tau of n would be a vector which is the normal traction minus sigma times n times n. What I have taken advantage of is the fact that the shear stress will be a vector in the plane of the cube. Okay, shear stress will be a vector in the plane of the in the plane which whose normal was n. Okay, so there are 2 components of the shear stress that is possible in the plane. 2 orthogonal components are possible to represent the shear stress. Okay, and this shear stress will be perpendicular to the normal direction. So, if I have 2 vectors which are normal to each other, I can subtract them to get the resultant vector. Okay. So, basically that is what I have used here. Now, the magnitude of shear stress would be magnitude of the normal stress squared minus sigma n squared. Okay. This again comes from the fact that the tau is perpendicular to the n here. Okay. So, from this I can get what is the shear stress in general. Okay. I have found already this. T of n is also something I found in the process. T of n is T's of n is this vector is T's of n, that is what we wrote here, T's of n is this vector. So, I have found that vector also. Okay. So, T's of n we have found, sigma n we have found. Now, we have to find the shear stress magnitude, which would be basically 10 sin 30 plus 3 cos 30 the whole square plus 3 sin 30 plus 5 cos 30 whole square, that is T's of n square, minus sigma n square was 10 sin square 30 degrees plus 5 cos square 30 degrees plus 3 into 2 into cos 30 into sin 30 the whole square, that will be tau of n squared. You can find this, you can do the computations to find what the magnitude of the shear stress is. Okay. Now, one way is to find the normal and shear stresses using the approach that I shown here. The other way is to go here and say that I am rotating this Ex by an axis to match with this normal n. Okay. So, the other approach is I add this Ex, Ey. Now, what I will do is I will rotate this axis to Ex star, Ey star, where this angle would be 90 minus 30, which will be 60 degrees, which is what the normal makes with the horizontal axis. Okay. That is the direction of the normal, and in this rotated system I will find sigma x star and sigma x star y star. This will be nothing but sigma of n, and this will be nothing but tau of n, magnitude of tau of n. Okay. So, you will find that both the approaches lead to the same value. Okay. So, I can use Mohr circle concepts, or I can use directly the fact that the normal stress is given by sigma transpose n dotted with n and shear stress is given by this expression to compute the stresses acting along a plane and normal to the plane. Okay. So, that is what you essentially learned in this lecture, how to compute the normal stresses acting along a plane given a stress tensor, and how do you compute the shear stresses acting along a plane given a stress tensor, and what is the maximum value of this normal stress and maximum value of this shear stress in 2-dimensional case. Okay. We will stop here for today. The next lecture will extend this what we assumed as plane stress to a 3-dimensional state of stress. Thank you.